Building Services Overview Part 2. In this session, we look at domestic hot water, heating controls, air conditioning and air handling units. Where does our hot water come from? Well, a lot of the time in our buildings it comes from the boiler, but there's been quite a move over to using instantaneous hot water systems and also small individual little hot water systems. But the most basic way of actually heating hot water is quite often just using an immersion heater in a tank, a well insulated tank. This works quite well, but probably not the cheapest way of producing hot water, but it's actually fairly simple. We just need an electric supply. We've got no gas flues to worry about or gas supplies. And as long as we're not using vast quantities of hot water, it's not necessarily a problem for the cost and the efficiency, etc. Now, if we're using hot water from a boiler, we tend to go into a cylinder and have a coil inside the cylinder which acts as a heat exchanger. We have a cylinder thermostat 1/3 of this the way up the cylinder, and that tends to control the temperature of the water by bringing the boiler on when the temperature at the thermostat reaches a lower temperature, triggers the boiler to come on and then tops up the cylinder. It's important though to make sure that this thermostat is set at least 60 to 65 degrees to kill off any harmful bacteria in the water. As we can see by this thermostat here, this one's set much too low. So sometimes it's false economy by thinking that we're going to set the thermostat low to make it more efficient. But obviously that might be a good idea, possibly not for scolding people, but obviously we need to think about the temperature for keeping the water hot to kill off any bacteria there. Now, lots of our domestic hot water systems are similar to what we have at home, but just the commercial ones tend to be a lot larger. The one on the left we can see there, although it says domestic style, it's definitely a commercial one. We can look at the fuse board and just look at the size of the cylinder and the pressure vessel. That's showing a pressurized system. On the top left of that left-hand picture is a pressure vessel that shows that it's an unvented system, so therefore it doesn't require a tank in the loft. Heating for that hot water cylinder is almost certainly coming from a boiler. We can see the coil going into it. Also, it's got an immersion heater that often acts as a backup as well. The pressure vessel on the left, that's to allows the water to expand so that obviously the tank doesn't sort of split due to the pressure there. On older systems, the water used to go up a vent pipe into the tank in the loft, and that was called a vented system. On the right hand side, that's a dedicated hot water boiler, might be in somewhere like a laundry or a kitchen, and we can see by the pipe labelling that gives us some idea of the temperature of the water. Blue, red, blue on pipe labelling means low temperature hot water, so water below 90 degrees generally. So as I said, we are tending to move away from the larger systems. The little standalone water heater or under sink water heater, as seen on the left there, tends to be favoured in quite a few locations now. Fairly simple to install, just requires a relatively small electric supply, a cold water supply. The good thing about this system is you don't get any standing water, so you don't get problems with the losses on the circulation loop and losses on dead legs. And also water standing in dead legs can be a problem for bacteria and Legionella disease there. Now, these standalone water heaters only really suit areas where we need quite a small amount of water. So it might be just for washing cups and washing hands and feeding 1 or 2 loos, etc. It's not the sort of amount of water we could have a shower or a bath under, because the actual heater itself doesn't contain that quantity of water. Usually 10 to 15 or even 20 litres of water, well insulated tank, so we don't tend to use lose any heat from them. This would be called a direct water heater. Also, the one on the right there is a direct water heater. It's a gas-fired one. Again, it might be somewhere where we use large quantities of water, like a laundry, a kitchen, etc. Now, we've got two sorts of hot water heating, either direct water heating or indirect systems. Now, the one on the left there generates them a bit like the standalone water heater there. Service water goes in, so cold water goes in, heated up in the heat generator, comes out hot. It's the same water heated up that goes in that comes out. Now, on the indirect system, the water in the heat generator, which is normally the boiler, never mixes with the service water. It just transfers heat via a heat exchanger, usually within a tank, could be a plate heat exchanger, but generally within a hot water cylinder there. We'll look at them in order. So there's our system controller, usually controls our boiler. If we've got a large system, we obviously have control through a BMS, but just on a small boiler, a small commercial system, one of the most important things on this is the time and the day setting and the date setting, because obviously if we're going to program our boiler to come on at a certain time, the time needs to correct, and so does the day. A controversial thing in offices, tends to be interfered with quite a bit, messed around with, people fiddle around to set it to higher temperatures or lower temperatures. Ideal temperature should be set on, as we discussed in the previous session, should be 21 or 22 degrees. But quite often it's a good idea to take this control away from the office, purely because it stops people fiddling around with the controller there. Another form of control is the thermostatic rad valve. Fairly basic control, allows us to sort of set our thermostats, our thermostatic rad valve to various levels, usually starting at 0, going up to 5, 0 being the coolest or quite often turned off, and 5 being the hottest. As I say, it is a fairly basic control. It's just a wax cartridge which operates a plunger inside the valve, and as the wax expands, it squashes the plunger, lets more heat in, etc., or restricts the flow. As I say, a fairly basic control, so don't really expect too much from them. Now, optimum stop starter, what's that? Well, quite often we get these in commercial buildings, probably don't know we've got them, usually operated through the BMS. It's the same sort of thing we'd have in a domestic system if you've got hive or nest. That tends to look at the temperature outside on the internet, depending on where you're situated. But on the optimum stop start on your BMS, it will look at the temperature outside your building, and it will bring on your heating system earlier or later so that it reaches the required set temperature at the time you want it to, showing at 7:30 on this particular slide there. If it's colder in the morning, it will bring the system on earlier. If it's not as cold in the morning, it will leave it till later, till it brings on the heating system. Tends to be a sensor on a north or a northeast facing wall that monitors the temperature first thing in the morning and sets our heating system up ready for the day. Now, boiler sequencer. Now, as we discussed in the previous sessions, boilers work better when they're working hard. So that's why we tend to have multiple boilers. But we don't want number one boiler starting up first every time. So the idea is we can sequence the boilers. So number one starts up 1 week, then number 2, then number 3, and then we can reverse the cycle. So we have 6, 5, 4, 3, 2, 1 going that way round. Most of the time that control is through the BMS, but it can be a manual control. Often says lead and lag on the panel. So we have a lead boiler and a lagging boiler. Now, most modern buildings, most modern large buildings have big systems. BMS controls the heating and the cooling systems and the HVAC systems. And in fact, it can control anything in the building. It can be as complex as we want it to be. However, the majority of BMSs significantly underperform for various reasons. Reasons being idea that not set up correctly. No one really on site understands how it works, and it's never been programmed to work to suit our building, etc. It can do fire alarms, escalators, sometimes linked into BMS there. More often than not, it contains our heating, cooling, fan coils, does the metering for us, looks at the AHU and all the things associated with our heating system. It can also control the lighting as well, but that's not always very common. One good function about the BMS, it allows us to look at schematics. So looking at those schematics, we can actually look at any set time of what's going on in the heating system. We can see on that sort of diagram there, we've got a cooling system, we've got a heating system. That will tell us if the cooling or heating is working. It will show us the set temperatures. We can see on that one there, we've got a certain amount of either full fresh air or partial fresh air via recirculating some of the air out the offices, and we can control the dampers on the BMS and see them close on the picture. What I would say with the BMS there, one word of warning, don't always believe the picture because it only tells us what it thinks is happening. I think occasionally you need to check on site to make sure that that is what is actually happening on site, to make sure the actuators are working and to make sure the controls are doing what we expect them to do. So look for places like where we might find the screens, in places like plant manager's office, and they might actually be in the plant room, etc. Or look on site for sensors such as BMS and Honeywell and Trend and Johnson's controls and names such as that. So cooling. A lot of our buildings nowadays have cooling. Well, why do we need cooling? Because I wouldn't say it's new, but we didn't have it years ago. But offices and work environments have changed considerably. Didn't have a lot of things in offices years ago that actually generated a vast amount of heat. But now we have things like servers and printers and computers, quite intense lighting and things like that. Although saying that, we have moved away from the tungsten lighting to LED lighting, so that tends to help for the lighting there. So we need cooling because heat is gained through the fabric. Not so much in this country because our walls tend to be well insulated. We do gain a lot of heat through solar though, through windows. People generate heat, computers, lighting, cooking, all of those things in our building generate heat. And if the total heat gain is more than the heat losses, the temperature continues to rise. So ideally, we want the temperatures to stay within reasonable limits. We don't ideally want to go below 22 or 23 because that would be quite excessive cooling and would be quite costly to do and also bad for carbon emissions. If we can get it to stay 23 and above, that's quite good for saving energy. So how can we achieve that cooling? Well, we could do it by natural or mechanical ventilation, and that's okay when the temperature outside is cool enough, so bringing in cold air. But depending on where our building is situated, if it's in a city centre where it's noisy and it's dusty and we get traffic fumes, bringing in fresh air is not going to be an option for us. Mechanical ventilation can bring in fresh air from the roof level. That can work quite well where the air is cleaner and we haven't got the noise problem. But again, if the air outside is too warm, that's not going to cool us. We could increase the thermal mass of our building, but that's not really an option because our building is either solid thermal mass or it's a light thermal mass. Generally, solid thermal mass buildings tend to be cooler because the thermal mass absorbs the heat from the building. Modern buildings tend to overheat quite quickly because there's nothing in the mass of the walls to absorb the heat. We could use evaporation like shown on the picture on the left there. You know, water running down that grass, evaporating away, cooling the glass, but that's really a bit messy. That's not going to work. What about Legionella disease and contamination of water, etc.? Or we could use refrigeration, which is what we tend to use in things like chillers and split system. The downside with refrigeration though is it uses energy, it requires maintenance, and most refrigeration systems contain refrigerant gases and they are quite damaging to the environment. And looking to the future, the government's looking to phase these gases out and is started to do so over the past few years. So we tend to use these things called splits and multi-splits. So what's a split or a multi-split? So a split system simply means we've got one unit outside and one unit inside, usually connected via two copper pipes, one large and one small, one high pressure and one lower pressure. Also, we have an evaporator drain as well, coming from the indoor unit to outside, and used an electrical cable as well, powering the indoor unit. So the main power comes from the outdoor unit, and that feeds the indoor unit. So inside them, we've got, in these systems, we have a compressor, a condenser, and an expansion device, and an evaporator. The compressor raises the pressure of a low temperature gas to a high temperature, high pressure gas. The condenser actually lowers the temperature, so we've now got a lower temperature, but we've got higher pressure. And then the expansion device expands the gas out into the evaporator, where it cools down and therefore absorbs heat from the room, thereby making our room cooler. As we can see on that diagram, leaves the compressor, ends up in the condenser, ambient air from outside is drawn across it, takes the heat out of the gas stroke liquid, because it's quite often changes phase at that point. And the warm air blowing out of the condenser is not the air from the room. Remember, on these systems, the air in the room never changes. It's just the warmth, it's the heat out of the room. Liquid then continues down to the evaporator, opens at the metering device, or the expansion device as it's sometimes called, expands into the evaporator, cools down, we draw the warm room air across it, it absorbs heat from the room air, leaving us then with cold supply air, and then continues its journey back to the compressor, where it goes through the cycle again. And it's actually quite efficient at doing this, and we'll look about how efficient it is in a minute. So there's the units on the left hand side, always come as a match set, and that's quite handy because it helps us identify the indoor and the outdoor units as a match set. So if you've got various makes on site, the units will always be, the outdoor, the indoor, and the controller will always be from the same manufacturer. Now on the right there, it's showing some split systems. We can actually use these split systems to do heating and cooling in our offices. Look at that as an installation. It's quite good there. It's quite handy for maintenance. But the trouble is, putting them near an outdoor car park is quite a bad thing, really, because we can get dirt from cars and from that motorbike in the picture there, and it's also could be susceptible to vandalism. The problem with moving them into a better area, such as on the roof, it makes them operate better. It's a cleaner environment up there, but it makes them difficult to service. So I think you need to balance one off against the other to whichever suits your location. My preference would be to put them on the roof and have good access onto the roof, either through the building ideally, so you can allow them to be serviced correctly. And then they're obviously not in harm's way, and they're in a cleaner environment. Now when we look at those units there, that doesn't necessarily give us a clue to what's on the inside. If we look at the inside, we've got the ducted split system, the ceiling mounted cassette, the wall unit, and the floor standing unit. All of them actually give us the same cooling rating, but the ducted and the cassette tend to give us better distribution. The wall unit tends to suit things like server rooms and perhaps smaller offices, doesn't distribute well into larger offices. And the floor standard unit generally don't work that well at all, because otherwise the cold tends to stay at the bottom, whereas on the ones above it drops the cold onto people, which is quite good. Also with the floor standers, they suck in at the bottom and blow out through the top, and they also tend to suck in anything else that's at floor level. So if we've got dust and debris and dirt on the floor, it tends to suck those in and block up fairly quickly. Now the cassette unit is quite a popular one in modern offices. We only tend to see the face of it. There's quite a substantial unit behind it, and it sits probably 200 to 300 mil into the ceiling there. We can see the pipes going into it, the larger pipe and the smaller pipe. The smaller pipe is the high pressure, and the larger pipe is the lower pressure coming back from the evaporator there. The filter is easily accessible through the grill in the center, because the air is sucked in through the center and distributed out through the 4 vents at either side. The wall mounted unit tends to give us more basic distribution. It sucks air in through the face, through the grill of the actual front of it, and blows air out through the vent at the bottom. Quite often the vents can oscillate just to try and spread the air out a bit better there. Tend to come with more basic handheld controllers rather than hardwired controllers. The ducted split system, although it's the better system out of all of them, tends to be quite difficult to get to swap the filters. And it's a shame that it's because they tend to be less well maintained because they're difficult to get to. So the better system tends to be not maintained as well. Now, a multi-split system, as the name would suggest, we've got one unit outside and multiple units inside. Easily recognised on the outdoor unit by the multiple pipe works there. You can see we've got 3 pairs of pipes. A single split would have 1 pair of pipes. A multi-split, on this one, we can see 3 pairs of pipes. So it's a 3-way multi-split. So there's our units. We've got different units there of different age and different efficiencies. The efficiencies of the air conditioning units is measured in something called energy efficiency ratio, EER. So we can see the one on the left, Samsung unit, energy efficiency ratio 3.4, modern Sanyo unit, EER of 3.1, old Airwell unit, EER 2.1, and a non-inverter Airedale 2.6. And what that means is for every kilowatt we put into them, we get out on the Samsung 3.4 and on the Airwell 2.1. So the Airwell is the oldest one, and really we ought to think about upgrading that. The other 3 are reasonably efficient. So where does that efficiency come from? If we look on the rating plate, we can see that this Sanyo unit here, it has a cooling capacity of 5.1 kilowatts, 5.15 kilowatts. It only uses 1.5 kilowatts of electricity. So therefore, divide the 1.5 into the 5.15 and it gives us an energy efficiency ratio of 3.43. So that's 340% efficient. In heating mode, it has a heating capacity of 6 and a COP, a coefficient of performance, and that's the heating equivalent of the energy efficiency ratio of 3.81. So therefore, it's 381% efficient in heating mode. And again, if we compare that with our boiler, which even our best boiler is about 92%, these split systems are quite efficient for heating. But again, don't forget that electric's expensive. It's 4 times more expensive than gas. So cost-wise, it probably just costs more to run. So rather than using split systems, we can in fact use what we think called variable refrigerant flow, VRFs. Lots of modern offices use these. VRF or VRV, if it was a Dakin, they refer to them as VRVs because that's just a trade name of Dakin, but they're all generically called VRFs. Invented by Dakin in 1982, ductless mini split system. And this is where we've got one outdoor unit, quite a large outdoor unit, serving multiple indoor units, usually working at varying speeds and driven by an inverter. Also, we've got what we call heat recovery technology, which we'll look at in a minute. Energy savings of up to 55% predictive over comparable splits and multi-splits, because when we run splits in our office, a single split, it only actually works independent. It works independent of anything else in the room. So we could be running a split in heating and running a split in cooling, and the two wouldn't relate to each other. What a VRF does, it actually talks to all the indoor units and it can move heat from one place to another. So what's a VRF? It's a multi-zone refrigerant split system, provides cooling and heat pump heating. Now remember, in lots of our buildings, to provide heating and cooling, we'd need a boiler and chiller. This VRF unit does both. It does heating and cooling simultaneously as well. So again, it's quite clever there. 2 or 3 pipe systems, variable capacity indoor units, which means our units can either be large or small, high turn down ratios, and that means that we can actually run it at quite a low setting. We can run it below 10% of its rating, and it can just be ticking over there. And it will also link in to our VRF, to our BMS system. We'll also get what we call a relatively straight set point out of it. So if we're not careful with split systems, they do tend to go up and down. So they go hot, they go cold, and that can tend to be quite an annoyance in office. What a VRS will tend to do is, if we've set it on 21, it will stay on 21 and have quite a straight set point there. Quite easily recognisable, we can see them here. They usually suck air in through the sides and discharge the air out through the top. Again, it's worth remembering, it's like the split systems, the air in the room with these systems never changes. So we need to have, generally coupled to a heat recovery system, such as VAMs or Losnays, or some sort of plate heat exchanger or thermal wheel, like we talked about in the previous session. So the unit sits outside, we can see on the bottom left there, communicates with the zone control valve or branch controllers, as they're sometimes called, and sends the heating and cooling to various indoor units, cassettes, and floor units, and even decorative roof panels there. Now, lots of offices require heating and cooling simultaneously, because on the top right there, we can see where we're providing cooling. That part of the office might be high IT, it might have a lot of solar gain and require cooling. Now, the other side of the office might be north facing, or it might have no IT in and might be quite cool, so it requires heating. And in fact, when we think of a cooling system, it doesn't actually provide cooling. What it does is absorb heat. And what it's doing in this picture, it's absorbing heat from the top left there and moving it to the area at the bottom right, at the bottom left, sorry, where it actually needs the heat. So it's moving it from the indoor units where it's providing cooling to the indoor units where it's providing heating. And we can get COPs and EERs as close to 4 can be achieved there. Now, what we've just mentioned there really is what we call comfort cooling. It's a fairly basic cooling, and again, the air in the room never changes. Now, with complex cooling, the air in the room tends to change, and the cooling is delivered quite often via the ventilation air. So we quite often use chillers. We can either use air-cooled chillers, water-cooled chillers, or absorption chillers. Absorption chillers are quite rare, and they work on excessive heat from somewhere. So they could work on excessive heat from a CHP or perhaps from some sort of process in a factory. Air and water-cooled chillers are both electrical powered, and the absorption chiller is powered from excess heat. Now, all 3 of those chillers cool water down and send it out into our building, where the water goes through air handling units, chill beams, fan coils, etc., and absorbs heat from the building, sends it back to the chillers where they process it, and the air-cooled chiller rejects heat out the top. The water-cooled chiller pumps away that heat, and it's rejected either through a dry air cooler or a cooling tower, usually again situated on the roof. And the same process with the absorption chiller. One thing it is a good idea to consider is trying to interrupt this, what I call the condenser circuit, going away from the water-cooled chiller, and rather than rejecting the heat, think, could we do something with that heat, sort of process it for perhaps underfloor heating or preheating domestic hot water, rather than just throwing that heat away on the roof there. So the air-cooled chiller, it contains all of the same components as our split systems, but actually tends to absorb the heat within the unit itself. And we can see on that one there, it's got 3 circuits. We can tell it's got 3 circuits. We can see the 3 switches under the heat exchangers on the top. It draws air in through the triangular holes in the side and blows them out through the fans in the top, absorbing the the coolness into the heat exchangers. This particular one is about 1,000 kilowatts, so they're quite hefty units, and this one weighs nearly 11 tons, so you do need quite a substantial building. This one worked in conjunction with 15 other chillers on a large department store in London, and they all fed into a single chilled water main. They do contain quite a lot of refrigerants, these chillers, and as you can see, this one in its 3 circuits, 85, 66 and 100 kilograms in individual circuits. So that's nearly 1/4 of a ton of refrigerant in this air-cooled chiller. The good thing about it though is if the actual refrigerant is not in the environment, is not in the area where people are. So if there was a problem, and hopefully there wouldn't be, and it leaked out, it would just leak into the environment, albeit it would damage the environment, but it wouldn't be contaminant to people there. Now most air-cooled chillers are quite large capacity units. We can see on the left though, that's a smaller unit, but we probably wouldn't confuse that with a split system. The one on the right though does look a bit like a split system, so that can be a little confusing for us. But if we look at the pipe work going away from it, it's fairly large bore pipe work, which sort of indicates it's water pipe work as opposed to refrigerant pipe work. So this is a small air-cooled chiller. Now, some of the modern air-cooled chillers do what we call free cooling, and that means that rather than actually going through the compressors and kicking the chiller into action and using lots of energy, it just looks at the ambient air temperature outside. And if the ambient air temperature outside is cool enough, it can just cool the water by drawing ambient air through the cooling coils into it and then sending that back into the building there. And doing so, it can actually get what we call an ESEER. That's a European Seasonal Energy Efficiency Ratio of 6.23. That means it's over 600% efficient. This particular unit uses a low global warming potential refrigerant, R1234ZE, and that's where a lot more modern chillers use that, and also a lot of our modern cars are going to swap from 134A and go to R1234ZE as a refrigerant there. Now, water-cooled chillers work on the same principle as air-cooled chillers, but actually tend not to reject the heat where the chillers are. They tend to reject the heat elsewhere. And the only reason you tend to use a water-cooled chiller is a lot of the time because you've got nowhere to put an air-cooled chiller. So water-cooled chillers sit in the basement and reject the heat, perhaps on the roof, and the air-cooled chiller tends to sit on the roof and reject the heat where it is there. And because of the fact that they're smaller, it actually means that we can put these water-cooled chillers in plant rooms and pipe away the rejected heat from them. Water-cooled chillers can be slightly difficult to recognise because they can resemble things like generators and water pumps. But here we've got 6 in a basement, again in a large department store in London, a different one than one before, connected to a cooling tower. So this one uses Legionella's dosing equipment, because if we're rejecting heat via a cooling tower, we need to be aware of any potential droplets containing Legionella's disease. What would be a good idea for our water-cooled chiller, like we mentioned earlier, is using some form of heat recovery, because rather than waste that heat, we could pass it through a heat exchanger and pump it back into our building and use it for underfloor heating or domestic hot water. Now, dry coolers and cooling towers. Now, this is a way of rejecting heat when we don't need it. It would be great to use that heat like we just mentioned previously, but if there's no way of using it on site, we can reject it via a dry cooler. They are finned heat exchangers used to reject heat from air conditioning plant or water-cooled VRFs, etc. They generally used in lieu of wet systems such as cooling towers, because cooling towers fell out of favour slightly because of the fact of the potential threat from Legionella disease. And basically dry air coolers are closed systems, so they have no Legionellas threat. Tends to work by drawing the air in through the bottom of the dry cooler. Water is pumped up from the water-cooled chiller, possibly situated in the basement, pumped up to the dry cooler. Air is sucked in through the bottom of the dry cooler, blown out through the top, using ambient air temperatures to cool the water. We can see on the one on the left here, they do suffer from sort of corrosion in the environment, and also people tend to spray them with water to make them work better. If we spray them with water and the water's got limescale in it, perhaps in London or Reading and those sort of areas, and in the Midlands as well is the same, the limescale can attack the aluminium fins, thereby causing damage to the unit. On the right there, that's a plate heat exchanger within a cooling plant. So rather than reject heat via the condenser, which we talked about earlier, it rejects its heat through a plate heat exchanger and therefore pumps that heat onto the dry cooler onto the roof. Now this is quite a substantial dry cooler, and actually these can be used for free cooling by using the ambient air temperature, possibly in this country perhaps 70% of the year, 70 to 75% is cold enough outside to actually just use ambient air temperatures. The advantages of the dry cooler: closed loop cooling, reduced water treatment cost, reduced corrosion of water systems, and also a safe alternative to cooling towers, etc. Cooling towers though. Heat rejection device which extracts waste heat to the atmosphere through the cooling of water basically through evaporation. Cooling towers do actually work really well. They work better than dry coolers, but a lot of people just won't use them because they do cost quite a considerable amount of money to maintain, and we do need to have regular testing and auditing of how we're treating the water and how we're potentially combating that Legionellas problem. And we can see on the bottom right though, cooling towers, if not maintained correctly, can in fact be quite messy. They do discharge quite a lot of water sometimes. We can get vegetation and sludge going around them, and because of that people just tend to shy away from them, and they have fallen out of favour in the past few years, unfortunately. And I say unfortunately because cooling towers do work really well, and they do work on really hot days where often dry coolers struggle. So they work by the hot water we can see there is pumped into the top of them, runs through the side panels, dry air is drawn in through the fan sits on top, draws the air in from the side, evaporation takes place, cooling the water down, and we end up with cold water in the collection basin at the bottom. Unfortunately, that moist warm air blowing out the top is just the right sort of temperature for Legionellas bacteria. If we are using cooling towers, again we need to regularly dose the water to make sure the water is treated, and it needs to be tested again on a regular basis and audited to make sure there is no problems. There's another form of cooling we can use, and it's called adiabatic air cooling. This is a bit of a hybrid system, a bit halfway between a cooling tower and a dry cooler. We actually spray water vapor out into the air that's being drawn into the dry cooler. As the air passes through the water vapor, it cools down through evaporation, and therefore the air hits the dry cooler that much colder and makes them work better in warmer temperatures. Right, air handling units. Found in most commercial buildings, and quite important thing, they tend to bring in all the fresh air in our building. Lots of buildings now don't have opening windows, and we need air handling units to bring in the fresh air. Usually a large metal box connected to some sort of ductwork, quite large ductwork, usually distributed around the building. Sometimes on smaller air handling units, they sit directly above the area which they feed, and they're called constant volume units. So these smaller air handling units often sit as a bit of a retrofit on older buildings where we might have sealed up the windows or decided opening the windows is not a good idea, and these can work in conjunction with VRFs and split systems, and these units bring in the fresh air. The one on the left is the supply and the one on the right is the extract. You generally find a supply and an extract because if we're pumping air in, we need to actually take stale air out. On larger buildings, we tend to get larger air handling units, and quite often the supply and the extract sit on top of each other. And that's usually where we have some form of heat recovery, like we looked at in the previous session, either using a plate heat exchanger or a thermal wheel. We can see that this air handling unit does hot and cold as indicated by the arrows on it. On larger buildings, such as perhaps local authority buildings, hospitals, large department stores, we have very large air handling units. These should be treated with caution because if we actually go in these to examine them or go in them to see if there's a problem, we really want to lock them off to make sure that they don't restart when we're in there. So we can see on the one on the right, it's got its own fuse board, it's even got its own lighting in there, and we can walk inside the units, but make sure they are safely locked off before we enter them. Now these rooftop units, these are the constant volumes ones that we mentioned earlier, where they sit directly above the space that they're feeding. Tend to be on places like supermarkets or perhaps distribution centres or large stores such as like the B&Qs and the Halfords and Decathlons and stuff like that. These do heating and cooling at the same time. Can be quite maintenance hungry because perhaps a large building could perhaps have as many as 20 on the roof, so therefore quite a big maintenance requirement there. Air handling units at data centres tend to resemble cupboards but still have the same components inside. Tend to have the filters at the top. As they draw the air in from the top, the air goes through the units, through the heat exchangers, and is actually pumped into an underfloor void where it feeds grills coming up through the floor, perhaps on the downflow and upflow systems. So what's in this air handling unit? We can see that the air comes in, first thing it hits is the filters. Next thing it hits is probably the heating coil. Now, then it hits the primary chilled water. Usually the chilled water comes from a chiller. The heating, more often than not, comes from a boiler. May go through a reheat coil. It's not a very efficient way of doing things. This is not cooling it down and heating it back up again, but it's generally put there to try and raise the humidity level again. Now the most important thing in this air handling unit is in fact the filters, because if the filters fail or if the filters let any dirt by or debris, it contaminates the heating and cooling coil. So filtration is almost always present in order to provide a clean, dust-free air to the building occupants. Typically faced in two banks. We have a fairly basic box filter, cardboard sort of filter, and then a more expensive bag filter. Quite often we can get away with leaving the bag filter in for an extra term if we actually swap the box filter fairly early, because the bag filters can tend to be quite expensive. Now we monitor the condition of the filters by a pressure differential gauge. We monitor the pressure either side the filter, and if the pressure is too great, depending on what the Pascal rating is set, so basically we're looking for a Pascal rating of probably over 80 to 90 or 100 Pascals on a fairly basic box filter. When it gets to that level, it then triggers the alarm on the BMS and tells us the filter is blocked. As we can see on this picture, this one is broken. They do get damaged quite easily. If you've got these at work, it's quite a good idea to check them quite often. The pipe work becomes quite brittle and the fittings become quite brittle as well. The one on the left here is the more basic visual manometer, and we can see that here that on the left pipe, that's the pressure before the filter, and on the right outlet on that unit, that's the pressure after the filter. And because the pressure is more on the left than it is on the right, it's pushing that liquid down that scale, and it's showing a reading there of about 90 pascals, which would indicate the filter is blocked. The gauge on the left is one that links into the BMS. That one's showing about 30 pascals, and that would indicate that the filter is new, because even a new filter has a certain amount of resistance. Now, failure to swap the filters at the required interval lead to their collapse, and then the air rushes over the top of the filters and contaminates the air handling unit. The one on the right there we can see has been left in for a considerable amount of time and is starting to break up. Now, filters again, like the one on the left there, can quite easily be dislodged. These particular filters are quite weak. They don't seem to have a frame around the outside, and quite easily get dislodged or pulled out with excess pressure. The fan in the air handling unit is quite strong. So when the filters become blocked with contaminants and dust and debris, etc., the fan then puts pressure on the filters and pulls them out. We can see there that that leads to contamination of the air handling unit, and that can actually cause quite a lot of damage in the air handling unit. So it's make sure that the filters are swapped on a regular basis so that the air handling unit remains clean inside. So most air handling units provide heating and cooling. Not all of them. Some of them just actually bring in fresh air. But if they're going to do heating and cooling, heating usually comes from boilers, cooling usually comes from chillers. Heating can actually come from electrical resistance. Quite often modern offices have electrical resistance heating, because modern offices tend not to need much heating in the office, mainly because the offices are getting all their heat from the people, the computers, the servers, the IT, and the photocopiers and printers and stuff like that. So a lot of the time they have electrical resistance heating, but it's quite often not used. So they use heating and cooling coils, usually manufactured from copper with aluminium fins. And we can see by that one on the left there how clean that actual fin is, how clean the fins are. And that looks like the day it left the factory. And it was quite an old unit, this. And it shows that with good maintenance and maintaining this regular, we can keep that quite clean. We can see how close the fins are and how delicate the fins are. If we let this get blocked up, it soon becomes overblocked, and therefore we don't get any airflow through it. So example there on failure to clean those units. We can see how the contaminants have all stuck to the face of the heat exchanger, and that will be quite difficult to remove now. It would have been better putting more effort into swapping the filters, and then we wouldn't be left with that problem of the heat exchangers blocked up there. So thanks for listening for this session. That was the end of part 2, and we'll see you on the next session. Thank you.